Hello there and welcome to ThinkSleep. Tonight, we're going to look up at the stars and ask something simple to say but not easy to answer. What if we're not the first to reach them? What if somewhere in the deep past civilizations developed the capability to slip free of Earth's gravity and navigate between worlds, only to vanish so completely that we've convinced ourselves we were the first to achieve spaceflight? I don't mean alien visitors or impossible technologies. I mean spacefaring capabilities that could have emerged from terrestrial intelligence, developed along paths we never considered, in times we've barely begun to understand. Before we begin this journey through the shadows of what might have been, I'd love to know where in the world you're listening from tonight and what time it is where you are. If this kind of gentle exploration appeals to you, I'd be grateful if you tapped like or subscribed. The idea that ancient civilizations might have achieved spaceflight sits uncomfortably with how we think about progress. We imagine technological development as a steady climb upward, each generation building on the last. But what if progress isn't a straight line but something more like a spiral, where civilizations rise and develop remarkable capabilities, only to fall so completely that their achievements become invisible to those who come after? When we talk about ancient history, we usually mean a few thousand years. The pyramids, the first written languages, the earliest cities, even human civilization itself only goes back about 10 or 12,000 years. That's almost nothing compared to Earth's true age. The planet has existed for about 4.5 billion years. Our species appeared only recently in that vast timeline. Most of Earth's history passed without any complex life at all. For billions of years, only simple organisms existed, gradually evolving toward greater complexity. The planet keeps no record of intelligence. Any mind that emerged and gazed at the stars might have left nothing behind. Here's something worth considering. The physics of space travel never changed. Gravity worked the same way millions of years ago. The math of orbits was always true, waiting to be discovered. The energy in chemical reactions, the laws of motion, all of it existed long before anyone could use it. The universe was always ready for spaceflight. The question is whether intelligence ever arose that could understand and apply these principles. And intelligence has been emerging for hundreds of millions of years in various forms throughout Earth's history. What if intelligence developed in something completely unlike us? Perhaps in ocean-dwelling creatures that understood fluid dynamics instinctively, or cave-dwelling beings with deep knowledge of geology, or species whose biology gave them insights into forces we struggle to measure. Such minds might have approached space travel entirely differently. Maybe they didn't need rockets. Maybe they grew biological vessels or discovered ways to manipulate natural forces we haven't found. We use metal spacecraft because that's what we know how to build. But it's not the only possible path. Biology might offer solutions. Unknown energy sources might exist. Methods that work with nature rather than against it. Time makes this possibility real. If intelligence emerges from complexity, and Earth has been building complexity for billions of years, then countless opportunities existed. Most would fail, but even one success matters. If even once in 100 million years some Earth intelligence reached space, everything changes. Space offers endless resources, abundant energy, escape from planetary disasters. A civilization established in space might never come back. Earth would become a memory, fondly recalled, but no longer needed. This changes how we see ourselves. Over billions of years, reaching for space might be a pattern that repeats. We might not be first. We might be the latest in a long series of minds that looked up, understood, and eventually let go of their birth world to drift among the stars. Long before we ever dreamed of rockets or satellites, before we understood that the lights in the sky were other worlds like ours, human beings were watching the heavens with an intensity and precision that still takes our breath away. They built monuments aligned to celestial events with an accuracy that rivals our modern instruments. They predicted eclipses centuries in advance. They tracked the wandering of planets through the zodiac with mathematical precision that wouldn't be matched again for thousands of years. The Great Pyramid at Giza aligns to cardinal directions with an error of less than 2 arc minutes. Stonehenge captures the complex 18.6-year cycle of lunar standstills. The Antikythera mechanism, pulled from an ancient shipwreck, contains gears calibrated to track the motions of the sun, moon, and planets with breathtaking sophistication. These aren't the works of people who occasionally glanced up at pretty lights in the darkness. These are the achievements of minds obsessed with understanding the clockwork of the cosmos. But what's most striking isn't just the accuracy of these ancient observations, it's their universality. From the stone circles of Britain to the astronomical alignments of Angkor Wat, from the precisely oriented temples of Egypt to the calendar systems of the Maya, cultures separated by vast distances and seemingly impossible gulfs of time developed remarkably similar approaches to understanding celestial mechanics. They knew things that should have been impossible to know from Earth's surface. The Dogon people of Mali described the orbital characteristics of Sirius B, a white dwarf star invisible to the naked eye, centuries before modern telescopes confirmed its existence. Ancient Mesopotamian texts record the orbital periods of planets with decimal precision that matches our current measurements. Hindu and Buddhist cosmologies describe timescales and cosmic distances that align eerily well with modern astronomy's understanding of the age and size of the universe. How did they know these things? The conventional explanation is patient observation over many generations, careful record-keeping, and mathematical insight. And certainly, that accounts for much of what we see. But it doesn't account for all of it. Some of the knowledge encoded in ancient texts and monuments seems to require not just observation from Earth, but perspective from space itself. Consider the Piri-Reis map, drawn in 1513 but based on much older sources. It shows the coastline of Antarctica with remarkable accuracy, including details of the land beneath the ice that weren't confirmed until the 20th century. How do you map a continent buried under miles of ice unless you can see it from above, from a vantage point high enough to penetrate the white covering and reveal the geography beneath? Or consider the Nazca lines, those enormous geoglyphs carved into the Peruvian desert, visible in their full complexity only from the air. Who were they made for? Who was meant to see them? The standard archaeological explanation is that they were ritual pathways, perhaps astronomical calendars laid out on the ground. But that explanation feels incomplete when you're looking down at them from an airplane, seeing how they transform the entire landscape into a kind of cosmic diagram, a message written large enough that it could be read from very, very far away. The knowledge embedded in these ancient works suggests something more than casual sky-watching. It suggests systematic exploration, methodical mapping, the kind of comprehensive understanding that comes not from looking up at the stars but from moving among them. And if that's true, then the question becomes who was doing the moving? The easy answer, the one that preserves our sense of being first, is to imagine visitors from other star systems, ancient astronauts from distant civilizations who shared their knowledge with primitive Earth cultures before departing for home. But there's another possibility, one that's both more radical and more conservative. What if the knowledge came from Earth itself, from terrestrial intelligences that had already made the journey upward and were sharing what they'd learned with those still bound to the surface. This would explain the universality of the knowledge, why similar astronomical insights appeared in cultures with no apparent contact. It would explain the precision of the observations, why ancient peoples seemed to know things that should have taken centuries of careful measurement to discover, and it would explain the strange vantage point implied by some of these ancient works, the perspective that seems to come from looking down rather than up. But if ancient Earth civilizations had achieved spaceflight, why did that knowledge disappear? Why did subsequent cultures have to rediscover the principles of astronomy, reinvent the mathematics of orbital mechanics, rebuild the infrastructure of space exploration from scratch? Perhaps because spacefaring civilizations don't stay planet-bound. Perhaps because once you learn to live between worlds, you don't come back except to visit. Perhaps because the knowledge of how to leave the world is not the same as the knowledge of how to live on it, and when the spacefarers departed, they took their expertise with them, leaving behind only monuments and maps and the memory of having looked down from the sky. The ancient texts often speak of ages when gods walked among humans, when the boundary between earth and heaven was more porous, when knowledge flowed freely between the terrestrial and the celestial realms. We read these as myths, as the products of imagination trying to make sense of natural phenomena. But what if they were history, distorted by time and translation, but rooted in real events, real encounters, real knowledge shared by those who had learned to navigate the spaces between stars? The precision of ancient astronomy might be evidence not of patient observation from below, but of systematic exploration from above. The monuments they left behind might be not just calendars and temples, but landing markers, navigation aids, communications arrays designed to maintain contact between Earth and sky, between the children of the planet and the children of space. And if that's true, then when we look up at the night sky and dream of reaching the stars, we might be remembering something deeper than curiosity. We might be remembering home. When we imagine technological development, we tend to think of it as a ladder with rungs that must be climbed in order. First fire, then agriculture, then metallurgy, then steam power, then electricity, then rockets. We see our own path as not just the way things happened, but the way things had to happen. But that's an assumption worth questioning, especially when we're considering whether ancient civilizations might have found entirely different routes to the stars. The technology gap question isn't really about whether ancient peoples were smart enough to build rockets. It's about whether rocket-based propulsion is the only way to leave a planet's gravity well. We developed our approach to spaceflight based on the materials we had available, the energy sources we understood, and the manufacturing techniques we'd mastered. But what if a different civilization, working with different constraints and different insights, had discovered completely alternative approaches? Consider how different our own technology might have been if we'd developed along different lines. If we'd never discovered fossil fuels, we might have focused more intensively on solar, wind and water power, possibly developing energy storage and conversion systems far more sophisticated than anything we have now. If we'd never developed metallurgy, we might have pushed biological engineering to extraordinary levels, growing materials with properties that exceed anything we can manufacture. There are hints in nature of technologies we've barely begun to explore. Some bacteria can metabolize metals and produce compounds with remarkable properties. Certain organisms can generate electrical fields, manipulate magnetic forces, or create materials stronger than steel using nothing but biological processes. Trees grow structures that can bear enormous loads, while remaining flexible enough to bend in wind, using engineering principles we're still trying to understand. What if an ancient civilization had developed along biological rather than mechanical lines? Instead of mining metal and burning fossil fuels, they might have cultivated organisms that could transform matter at the molecular level, producing any substance they needed through guided biological processes. Instead of building rockets, they might have grown vessels that could survive in vacuum, navigate using biological sensors more sensitive than our instruments, and sustain their crews through integrated ecosystems that recycled everything perfectly. Such biotechnology wouldn't leave the kinds of traces we know how to look for. No metal debris, no chemical signatures from combustion, no radioactive isotopes from nuclear processes. The remains of biological spacecraft would decompose like any other organic matter, returning to the carbon cycle without leaving obvious artifacts. But the principles behind such technology would be reproducible by any civilization that understood biology deeply enough to direct evolution rather than simply observe it. There are other possibilities that don't require biology at all. What if gravity manipulation were possible through principles we haven't discovered? Our current understanding of physics suggests that warping space-time requires enormous masses or energies, but our current understanding has been wrong before. Every major breakthrough in physics has revealed that reality operates differently than we thought, that possibilities we considered impossible were simply waiting for the right insight. If an ancient civilization had discovered some form of field propulsion, some way to interact directly with gravitational or electromagnetic fields, their spacecraft might have operated on entirely different principles. No need for chemical rockets throwing mass in one direction to achieve thrust in the other. No need for the enormous fuel requirements that make our current space exploration so expensive and limited. The energy question is perhaps the most interesting of all. Chemical rockets are terribly inefficient, converting only a tiny fraction of their fuel into useful thrust. Even our most advanced propulsion systems waste enormous amounts of energy. But what if there were better approaches? What if previous civilizations had learned to tap energy sources we haven't discovered, or hadn't thought to use for propulsion? The Earth itself is a vast energy reservoir. The rotation of the planet, the circulation of the oceans, the movement of the atmosphere, the flow of heat from the core to the surface, all of these represent enormous amounts of energy. Most of it is too diffuse or too steady for us to harness effectively with our current technology. But a civilization with a deeper understanding of energy conversion might have found ways to tap these planetary systems directly. Or consider consciousness itself. We don't understand how awareness arises from matter, how intention translates into action, how observation seems to affect quantum systems. If these phenomena involve energies or forces we haven't identified, then a civilization that understood consciousness more deeply might have access to propulsion methods that seem impossible from our current perspective. This isn't necessarily mystical thinking. It's simply recognition that our technology is based on our current understanding of physics, and our understanding has changed dramatically many times in the past few centuries. Each time, what seemed impossible became routine. What appeared to violate natural law turned out to operate according to deeper principles we hadn't yet discovered. The point isn't that ancient civilizations definitely had access to exotic propulsion systems. The point is that our current approach to spaceflight might be neither the only way, nor even the best way to leave a planetary surface. If intelligence has arisen multiple times on Earth over millions of years, each iteration might have developed along completely different technological lines, discovering principles and possibilities we haven't even imagined. And if they did reach space using radically different methods, the traces they left behind might be so unlike what we expect that we wouldn't recognize them as evidence of technology at all. We might walk past their launch sites without noticing. catalogue their propulsion systems as unusual geological formations, classify their navigation aids as natural curiosities. The technology gap, in other words, might not be a gap at all. It might be a difference so profound that we lack the conceptual framework to bridge it, like trying to explain computers to someone who had never seen electricity, or describing music to someone who had never heard sound. When archaeologists first encountered the massive stone blocks at Baalbek in Lebanon, some weighing over 800 tons, they faced a puzzle that still hasn't been completely solved. How were stones of such enormous mass quarried, transported, and lifted into place with what we assume were primitive tools? The conventional explanation involves ramps, rollers, and vast numbers of workers, but the mathematics are troubling. The energy requirements are staggering, the logistics almost impossibly complex. Similarly, the precision of the joints at Sacsayhuaman in Peru, where massive stones fit together so perfectly that you can't slide a knife blade between them, suggests manufacturing tolerances that challenge our assumptions about ancient capabilities. The blocks aren't just heavy, they're cut and shaped with an accuracy that would be difficult to achieve even with modern equipment. These aren't isolated examples. Around the world we find megalithic sites that share certain puzzling characteristics. Enormous stones moved over great distances, precision cutting and fitting that exceeds what should be possible with available tools, and engineering solutions that seem to require understanding of principles we assume weren't discovered until much later. The standard archaeological explanation is always the same: human ingenuity, unlimited time, and vast numbers of workers can accomplish anything, and certainly that accounts for most ancient construction. But some sites push this explanation to its breaking point, requiring us to assume levels of organization, precision, and technological capability that seem inconsistent with the other evidence we have about these cultures. What if we're looking at this backwards? What if these exceptional sites weren't built by people struggling with primitive tools, but by people who had access to technologies we don't recognize as technological? What if some ancient civilizations had developed construction methods so different from ours that we can't identify them, leaving us to puzzle over the results without understanding the process? Consider the possibility that advanced materials science might not require industrial manufacturing. Biology produces materials with extraordinary properties through processes we're only beginning to understand. Spider silk is stronger than steel by weight. Abalone shells are tougher than ceramic armor. Tree roots can crack solid rock by growing slowly but persistently in the right places. An ancient civilization with deep biological knowledge might have developed construction techniques based on directed growth rather than cutting and assembly. Instead of quarrying stone blocks, they might have cultivated organisms that could shape rock through controlled erosion or mineral deposition. Instead of lifting enormous weights, they might have found ways to make materials temporarily lighter, or to manipulate the forces acting on them. The traces of such techniques wouldn't look like tool marks or construction debris. They might look like unusual mineral formations, strange erosion patterns, or biological processes that have been guided in subtle ways. We might be looking at the results of biotechnology and assuming they were achieved through brute force. There's also the question of acoustic engineering. Many megalithic sites have unusual acoustic properties. The King's Chamber in the Great Pyramid resonates at specific frequencies. Stone circles often exhibit acoustic focusing effects. Certain temples amplify sound in precise ways. We usually interpret these as happy accidents or minor design considerations, but what if acoustic manipulation was central to the construction process itself? Sound can move matter. Focused sound waves can levitate small objects, break apart materials, or cause them to flow like liquids. If ancient builders had mastered acoustic engineering to a degree we haven't yet achieved, they might have used sound-based techniques for quarrying, shaping, and positioning massive stones. The precision we see in ancient construction might reflect not mechanical accuracy, but acoustic precision. The ability to use sound waves to manipulate matter at the molecular level. Such techniques would leave almost no archaeological trace. Sound waves don't fossilize. The equipment for generating and focusing them could be relatively simple, perhaps just specially shaped chambers and resonating stones. The knowledge required would be mathematical and experimental, exactly the kinds of understanding that could be passed down through oral tradition without requiring written records. Then there's the mystery of the sites themselves. Why build with such massive stones at all? Our modern construction techniques favour lighter materials, steel frameworks, concrete that can be poured into forms. We use heavy materials only when absolutely necessary. But ancient builders often chose the most difficult possible approach, as if the enormous weight and perfect precision were not obstacles to overcome but goals to achieve. What if the mass and precision weren't incidental to the purpose of these structures, but essential to it? What if these sites were not just buildings but machines, designed to interact with forces we don't fully understand? The acoustic properties, the astronomical alignments, the massive scale, the precise geometry, all of these might have been functional requirements for some purpose we haven't identified. If ancient civilizations were spacefaring, their most important installations might not have been cities or temples, but launch facilities, navigation aids, or communication systems. The massive stone construction might have been necessary to provide stable platforms for equipment that had to maintain precise positioning relative to celestial bodies. The acoustic properties might have been designed to generate or focus energy fields used in propulsion systems. The precision cutting and fitting might reflect not primitive obsession with craftsmanship, but sophisticated understanding of how slight imperfections in structural alignment could affect the performance of sensitive instruments. When you're building equipment meant to navigate between planets, tolerance for error approaches zero. From this perspective, the megalithic sites around the world might be the remnants of an ancient space program, built to last through geological time, designed to function long after their creators had moved on to other worlds. The mysterious chambers and passages, the complex internal geometry, the careful orientation to celestial events, all of this might make perfect sense if we understood what these structures were really meant to do. We approach them as archaeologists studying dead civilizations, but what if they were built by people who expected to return someday? What if they're not monuments to the past, but infrastructure for a future we're not yet ready to understand? Throughout human history, in every culture, in every corner of the world, we find stories of beings who came from the sky. They arrive in chariots of fire, in boats that sail among the stars, in vehicles that shine like the sun and move without touching the ground. They descend from the heavens bearing gifts of knowledge, teaching agriculture, astronomy, the arts of civilization. Then, when their work is done, they return to the sky, leaving behind only memory and the promise that someday they will come back. We call these stories mythology, folklore, the products of imagination trying to make sense of natural phenomena that early peoples couldn't understand. But the universality of these tales is striking. Cultures separated by vast oceans and thousands of years tell remarkably similar stories about sky gods, celestial visitors, and the time when heaven and earth were more closely connected. The details vary, but the core elements remain consistent across continents and centuries. The Sumerian Anunnaki descended from the heavens to teach humanity the arts of civilization before returning to their celestial home. Hindu texts describe vimanas, flying vehicles piloted by gods and heroes, complete with technical specifications that sound surprisingly like aircraft manuals. The Book of Ezekiel contains detailed descriptions of a craft with wheels within wheels, powered by some form of energy that produced light and sound. Native American traditions speak of star people who came from the sky, lived among humans for a time, then returned to their home in the celestial realm. The conventional explanation is that these are archetypal stories, expressions of universal human psychological patterns rather than historical accounts. Early peoples looked up at the movements of celestial bodies and personified them as gods and heroes. The stories of sky gods reflect humanity's eternal desire to understand their place in the cosmos, to feel connected to something larger than their earthly existence. And certainly that explains much of what we see in these myths. But it doesn't explain everything. Some of the details are oddly specific, technically precise in ways that seem to require direct observation rather than symbolic imagination. When ancient texts describe the internal layout of flying vehicles, the materials they're made from, the sounds they produce when operating, the visual effects of their propulsion systems, we're looking at something that goes beyond archetypal storytelling. The Mahabharata describes aerial battles fought with weapons that sound remarkably like missiles and energy beams. The Ramayana gives detailed accounts of long-distance flights, navigation systems, and landing procedures. These aren't vague poetic descriptions but technical manuals, complete with operational instructions and maintenance requirements. Either the ancient authors had extraordinarily sophisticated imaginations, or they were describing something they had actually witnessed. There's also the curious consistency of certain details across cultures that had no apparent contact with each other. The idea of beings from the sky who mate with humans, producing hybrid offspring. The concept of celestial vehicles that can travel between worlds. The notion that advanced knowledge was given to humanity by visitors from above, then partially lost when those visitors departed. These consistent elements could represent universal human concerns about origins, knowledge, and our relationship to the cosmos. But they could also represent shared memories of actual events, cultural recollections of encounters that really happened, passed down through oral tradition and eventually written into sacred texts and mythological cycles. If ancient Earth civilizations had achieved spaceflight, returning periodically to check on the development of surface cultures, these myths might be distorted historical accounts of those visits. The sky gods might have been spacefaring humans, so technologically advanced compared to ground-based civilizations that they seemed divine. The gifts of knowledge they brought might have been real transfers of information from space-based to planet-based cultures. This would explain why the myths consistently portray the sky beings as similar to humans but more advanced, rather than as completely alien entities. It would explain why the knowledge they shared was always practical, focused on agriculture, astronomy, metallurgy, and other technologies that would help surface civilizations develop more quickly. It would explain why they're described as having emotional connections to humanity, caring about human welfare in ways that abstract gods or alien visitors might not. It would also explain the recurring promise of return. Throughout these mythological traditions, there's the suggestion that the sky beings will come back someday, that the separation between heaven and earth is temporary. This might not be religious hope, but practical expectation, the cultural memory of people who knew that their spacefaring relatives would eventually return to check on their progress. The myths often describe a golden age when the sky beings lived among humans, when knowledge flowed freely between the terrestrial and celestial realms, when the boundary between earth and heaven was permeable. Then something happened, some catastrophe or decision that caused the sky beings to withdraw, leaving humans to develop on their own. The world became smaller, darker, more limited. From a technological perspective, this pattern makes sense. A spacefaring civilization might maintain contact with planet-based cultures for a time, sharing knowledge and resources. But eventually the space dwellers would face a choice. Either bring the entire planetary population into space, or step back and let them develop independently. The first option might be impossible due to resource limitations or cultural differences. The second option would inevitably create the kind of separation described in the myths. The sky gods had to leave not because they were finished with their work, but because continuing to help would prevent humans from learning to help themselves. The withdrawal wasn't abandonment but graduation, a recognition that surface cultures needed to find their own way to the stars rather than being carried there by others. If this interpretation has any validity, then the myths might be more than stories about our relationship with the divine. They might be cultural memories of our relationship with our own future, accounts of what we might become if we successfully make the transition from planetary to space-based civilization. The sky gods might not be gods at all, but ourselves, seen from the perspective of those we left behind. In 1950, the physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos and posed a question that has haunted us ever since. If the universe is so vast, so old, so full of potentially habitable worlds, then where is everybody? Why don't we see clear evidence of other civilizations? Why does space seem so empty, so silent, so devoid of the radio chatter and technological signatures we might expect from a galaxy teeming with intelligence? This is the Fermi paradox, and it cuts to the heart of our assumptions about life, intelligence, and our place in the cosmos. But there's a version of this paradox that's even more unsettling, one that brings the question much closer to home. If intelligence can arise naturally from complexity, if spaceflight is achievable by technological civilizations, if the Earth has been a stable platform for life for billions of years, then why don't we see evidence of previous spacefaring civilizations right here on our own planet? The usual answer is that we're the first, that intelligence capable of space travel is so rare, so difficult to achieve, that it has happened only once in Earth's entire history and we're it. But that answer carries some uncomfortable assumptions. It assumes that the specific sequence of events that led to human civilization was not just unlikely, but virtually unique. It assumes that intelligence, once achieved, naturally leads to space travel, and that space travel, once achieved, leaves permanent and obvious traces. But what if those assumptions are wrong? What if intelligence has arisen multiple times on Earth, and some of those previous civilizations did achieve spaceflight, but in ways that don't match our expectations? What if the silence we hear when we listen for evidence of ancient astronauts isn't proof of their absence, but a result of our listening for the wrong kinds of signals? The Fermi paradox, applied to Earth's deep history, reveals something troubling about our investigative methods. We're looking for evidence of ancient space travel using the same assumptions we use to search for extraterrestrial intelligence. We expect to find radio transmissions, metal artifacts, chemical signatures of industrial processes. We assume that any spacefaring civilization would have developed along technological lines similar to our own, would have faced the same challenges we face, would have solved them in ways we can recognize and understand. But evolution doesn't repeat itself exactly. Intelligence arising at different times, in different environmental contexts, among different species, would likely develop different approaches to the same fundamental problems. A civilization that evolved in the ocean might understand fluid dynamics and pressure systems in ways that led to propulsion methods we haven't imagined. A civilization that evolved in caves might understand geology and material science from perspectives we can't access. A civilization that evolved in forests might integrate biological and technological approaches in ways we're only beginning to explore. Such civilizations might achieve spaceflight without ever developing radio technology, might reach other planets without leaving the kinds of chemical signatures we know how to detect, might establish space-based infrastructure without building the orbital debris fields we expect to see. Their approach to the problem might be so different from ours that their solutions would be invisible to our current search methods. There's another possibility that's even more unsettling. What if previous spacefaring civilizations succeeded so completely that they didn't just leave the planet temporarily, but permanently? What if achieving spaceflight is not just a technological milestone, but a kind of graduation? A transition from planetary to cosmic existence that's essentially irreversible? This would explain the silence perfectly. Once a civilization becomes truly space-based, once it learns to extract resources from asteroids, harness energy from stars, build habitats in the vacuum between worlds, it would have no reason to maintain a significant presence on its planet of origin. The planetary surface would become a historical curiosity, perhaps visited occasionally but no longer home. Such a civilization might monitor its homeworld from a distance, might even intervene occasionally in planetary events, but it wouldn't maintain the kind of constant presence that would leave obvious archaeological traces. From the perspective of planet-bound observers, they would appear to have vanished, leaving behind only legends and the occasional unexplained anomaly. This interpretation transforms the Fermi paradox from a question about why we don't see alien civilizations to a question about why we don't recognize the signs of our own graduated ancestors. The universe might not be empty at all. It might be full of space-based civilizations that arose from planets throughout the galaxy, but they exist in a realm so removed from planetary concerns that they're essentially invisible to us. The silence we hear might not be the absence of intelligence, but the sound intelligence makes once it has learned to truly listen to the cosmos rather than to the small concerns of individual worlds. The emptiness we perceive might not be void, but fullness of a kind we don't yet have the senses to perceive. From this perspective, our own drive towards space exploration takes on a different significance. We might not be pioneering a new frontier, but following a path that has been walked many times before, by minds that arose from this same world millions of years ago. Our rockets and satellites and space stations might be the first tentative steps in a journey that will eventually take us so far from our origins that future Earth-bound civilizations will wonder, as we do now, whether they are truly alone. The answer to the Fermi paradox applied to Earth might be that we are not alone, and never have been. The intelligence that once walked among the stars simply learned to walk so far and so well that they became indistinguishable from the darkness between worlds, present everywhere but visible nowhere, like the cosmic background radiation itself, the faint echo of origins transformed into something vast and patient, and utterly beyond our current ability to comprehend. When we think about what space travel actually requires, we tend to focus on the dramatic moments, the roar of rockets, the complexity of orbital mechanics, the precision of navigation between worlds. But beneath all of that spectacle lie some fundamental physical realities that any spacefaring civilization, ancient or modern, would have to address. The question isn't whether these requirements have changed over millions of years. They haven't. The question is whether there might be radically different ways to meet them. At its most basic level, space travel requires three things: enough energy to overcome planetary gravity, some way to survive in the vacuum and radiation of space, and a method of navigation between worlds. Our current approach tackles these challenges through chemical propulsion, sealed metal vessels, and electronic guidance systems. But physics doesn't mandate these specific solutions. It only sets the boundaries within which any solution must operate. Consider the energy problem first. Chemical rockets are actually a fairly inefficient way to leave Earth's gravity well. They have to carry their own fuel, which adds mass, which requires more fuel, creating a tyrannical equation where most of your energy goes into lifting fuel rather than payload. We use this approach because we understand chemical combustion well, and because it can generate thrust quickly when needed. But there are other energy sources that dwarf chemical reactions. The Earth's magnetic field contains enormous amounts of stored energy. The planet's rotation represents kinetic energy on a massive scale. The temperature differential between the planet's core and its surface drives convection currents that move continents. Solar radiation bathes the planet in more energy every day than human civilization uses in a year. Most of these energy sources are too diffuse or too steady for us to harness effectively with current technology. But a civilization with a different understanding of energy conversion might have found ways to tap them directly. Instead of carrying fuel, they might have learned to extract energy from planetary systems themselves, using the Earth as a kind of launching pad that provides the power needed for departure. Biological systems offer another approach entirely. Many organisms can generate electrical fields, concentrate metals from dilute solutions, or produce materials with extraordinary properties through processes that operate at room temperature using readily available materials. A civilization that understood biology more deeply than we do might have developed propulsion systems based on scaled-up biological processes, using living components that could adapt to changing conditions and repair themselves during long journeys. Such biomechanical spacecraft wouldn't just be vehicles but ecosystems, self-contained worlds capable of supporting their crews through biological cycles, rather than mechanical life support systems. They might grow rather than being built, mature rather than being manufactured, reproduce rather than being replaced when worn out. The survival challenge presents similar opportunities for alternative approaches. We protect ourselves from vacuum and radiation using metal hulls and complex environmental systems because that's what our industrial base can produce reliably. But many organisms have evolved sophisticated protection against environmental extremes. Some can survive complete dehydration, others can repair radiation damage faster than it accumulates, still others can enter states of suspended animation that last for years. A civilization that had mastered biological engineering might have developed spacefaring organisms that could survive vacuum exposure, metabolize radiation for energy, or create their own protective environments through biological processes. The boundary between spacecraft and crew might have been blurred or eliminated entirely, with travelers becoming part of their vessels rather than passengers within them. Navigation presents perhaps the most interesting puzzle. We use electronic instruments to measure our position relative to celestial bodies and calculate trajectories using complex mathematics. But many animals navigate using senses we barely understand, detecting magnetic fields, polarized light, infrasonic vibrations, or chemical gradients with extraordinary precision. Birds can navigate across thousands of miles using nothing but their innate sense of magnetic direction. Sea turtles return to their birthplace after decades of ocean wandering. Salmon find their way back to the exact stream where they were born using chemical traces so faint our instruments can't detect them. These biological navigation systems might be far more sophisticated than anything we've developed artificially. A spacefaring civilization that had evolved from oceanic or aerial species might have developed navigation techniques based on sensing gravitational fields, solar radiation patterns, or the subtle signatures of different worlds. They might have navigated between planets the way migrating animals navigate on Earth, using innate senses rather than external instruments. The propulsion systems of such a civilization might have operated on principles we haven't discovered or haven't thought to apply to spaceflight. If consciousness interacts with quantum systems in ways we don't understand, if biological processes can manipulate fields and forces we can barely detect, if there are energy sources in living systems that we haven't identified, then the possibilities for alternative approaches to space travel expand enormously. The traces left by such technology would be completely different from what we expect to find. No chemical residue from rocket fuel, no metal debris from failed launches, no electronic signatures from guidance systems. The archaeological evidence might look biological rather than technological, like the remains of organisms rather than machines. And if such civilizations had existed, if they had solved the challenges of space travel through biological rather than mechanical means, their success might explain why we find so few traces of them. Biological materials decompose. Living systems adapt and change over time. Even their spacecraft might have evolved beyond recognition, or returned to the planetary ecosystem when their missions were complete. We might be looking for the wrong kinds of evidence entirely, searching for metal when we should be looking for biology, for chemistry when we should be looking for life, for machines when we should be looking for evolution itself pressed into service as a spacefaring technology. If an ancient civilization had achieved spaceflight and then vanished from Earth's surface, what traces might they have left behind? Not the obvious ones we imagine, not the metal hulks of crashed spacecraft or the concrete pads of ancient launch sites, but subtler signatures, the kinds of evidence that might survive millions of years of geological recycling, while remaining just ambiguous enough that we could easily overlook them or explain them away. The most durable traces would likely be chemical rather than physical. Any civilization advanced enough for space travel would have had to solve complex materials problems, and their solutions might have involved creating substances that don't occur naturally on Earth. These synthetic compounds, if they were stable enough and produced in sufficient quantities, might still be detectable in certain geological layers. We already see this principle at work in our own geological impact. The synthetic isotopes from nuclear testing, the microplastics from industrial production, the altered carbon ratios from fossil fuel combustion, all of these are creating chemical signatures that will be readable in sediment cores for thousands, possibly millions of years. An ancient spacefaring civilization might have left similar markers, chemical fingerprints of industrial processes we don't recognize as technological because we achieved the same results through different methods. Consider the rare earth elements that are essential for modern electronics. A spacefaring civilization would likely have needed similar materials for their guidance systems, communication equipment, and energy storage devices. But instead of mining these elements from terrestrial deposits, they might have harvested them from asteroids, or concentrated them from seawater using biological processes. Such activities could leave traces in the geological record, unusual concentrations of rare elements, in patterns that don't match known natural processes. We might find these anomalies and classify them as unexplained mineral formations, never suspecting that they represent the waste products or processing sites of ancient space technology. The isotopic signatures might be even more telling. Different stellar environments create different ratios of isotopes, so materials imported from space often have isotopic compositions that don't match terrestrial norms. If an ancient civilization had been mining asteroids or processing materials from other worlds, they might have inadvertently introduced non-terrestrial isotopic signatures into Earth's geological record. We would probably notice such anomalies if we found them, but would we interpret them correctly? Our first assumption would be that they represent contamination from meteorite impacts or unusual geological processes. The possibility that they represent evidence of ancient space-based mining operations would be considered only after exhausting more conventional explanations. The propulsion systems themselves might have left detectable traces. Chemical rockets produce characteristic combustion products, specific ratios of elements and compounds that reflect the fuel and oxidizer combinations being used. But more exotic propulsion methods might leave even stranger signatures. If ancient spacecraft used some form of field propulsion, the energy fields involved might have altered the atomic structure of nearby materials in ways that would still be detectable. If they used antimatter for fuel, the annihilation reactions would have produced gamma radiation with specific energy signatures, possibly leaving traces in materials that were exposed to those fields. Even biological propulsion systems might leave chemical evidence. Living organisms produce characteristic waste products, specific organic compounds that reflect their metabolic processes. Space-adapted organisms might have produced waste products that don't match anything in the current terrestrial biosphere. Exotic biochemistries that would stand out clearly if we knew to look for them. The navigation and communication systems of ancient spacecraft might have required materials with very specific electromagnetic properties. Creating such materials often involves doping semiconductors with precise concentrations of foreign elements, or growing crystals with unusual lattice structures. The production waste from such processes might still be embedded in certain geological formations, waiting to be recognized for what it represents. There's also the question of infrastructure. Any spacefaring civilization would have needed launch sites, manufacturing facilities, and resource processing centers. While the structures themselves might have vanished, their environmental impacts could persist much longer. Large-scale construction projects alter drainage patterns, soil chemistry, and local ecosystems in ways that can remain visible for millions of years. Strip mining leaves scars that erosion can obscure but rarely eliminates entirely. Industrial processing creates chemical gradients in groundwater that can persist long after the facilities that created them have crumbled to dust. We might be looking at the environmental consequences of ancient space programs without recognizing them as such. Unusual soil compositions, altered groundwater chemistry, or modified landscapes that we attribute to natural processes might actually represent the long-term effects of activities we can't imagine, because we haven't developed the technology to undertake them ourselves. The most intriguing possibility is that some of the traces might still be functional. If an ancient civilization had built automated systems designed to operate for geological time periods, some of those systems might still be running, carrying out their original programming millions of years after their creators departed. Such systems would necessarily be very different from our current technology. They would have to be self-repairing, adaptive to changing conditions, and capable of using readily available materials for maintenance and fuel. They might look more like evolved organisms than manufactured devices, biological systems that had been modified for specific technological purposes. We might encounter such systems regularly without recognizing them as artificial. They could be integrated so thoroughly into natural ecosystems that they appear to be just unusual species or geological formations. Their activities might be so subtle so well matched to natural processes that we never suspect they represent technology at all. The traces left by ancient spacefaring civilizations might be all around us, embedded in the chemistry of rocks, the composition of soils, the isotopic signatures of minerals, the unexplained patterns in biological and geological systems. They might be hiding in plain sight, waiting not for better instruments to detect them, but for better theories to interpret what we're already seeing. The ocean covers more than 70% of Earth's surface, yet we've explored less of it than we have of the Moon. Beneath those waters lie landscapes as varied and dramatic as any found on land. Mountain ranges taller than the Himalayas, canyons deeper than the Grand Canyon, plains that stretch for thousands of miles without interruption. And all of it has been hidden from direct observation for most of human history, accessible only to the few creatures adapted to survive in that alien environment. If an ancient civilization had been primarily oceanic, if their cities and spaceports had been built on what were then dry continental shelves or shallow seas, most of their traces would now lie beneath miles of water and sediment. The rise and fall of sea levels over geological time has been dramatic and relentless. During ice ages, the ocean surface dropped by hundreds of feet, exposing vast areas that are now submarine. During warm periods, the waters rose to levels higher than today, flooding regions that are now dry land. This constant change means that any coastal civilization, no matter how advanced, would have had to cope with rising and falling waters throughout its existence. Their most important installations might have been built in areas that were dry land when they were constructed but are now deep ocean floor. Their launch facilities might lie under the abyssal plains, their manufacturing centres buried beneath miles of accumulated sediment. The ocean is not a passive repository. It is an active, dynamic system that processes everything that enters it. Salt water is corrosive to most materials. The pressure at depth can crush even the strongest structures. Ocean currents redistribute sediment constantly, burying some things while exposing others. Marine organisms break down organic materials and colonize any available surface. The ocean floor is constantly being recycled through the process of seafloor spreading, where new crust forms at mid-ocean ridges, while old crust is subducted at oceanic trenches. This means that anything deposited on the ocean floor has a limited lifespan. The oldest oceanic crust is only about 200 million years old, much younger than the continents. If an ancient spacefaring civilization had operated more than 200 million years ago, most of their oceanic infrastructure would have been recycled back into the Earth's mantle, melted and reprocessed beyond any possibility of recognition. But even more recent traces would be difficult to detect and interpret. The deep ocean is largely unexplored because it is so difficult and expensive to reach. We have better maps of Mars than we do of our own ocean floor. The few areas we have surveyed in detail reveal a landscape full of unusual formations, perfectly round holes in the seafloor, geometric patterns in sediment, straight-line features that stretch for miles, formations that look artificial but are assumed to be natural because we can't imagine any other explanation. Some of these formations might indeed be natural, products of geological processes we don't fully understand, but others might be the remains of ancient infrastructure, so altered by time and environment that we can't recognize their artificial origin. A launch pad might now appear to be an unusual crater, a manufacturing facility might look like a mineral deposit, a communication array might resemble a volcanic formation. The challenge is compounded by the way we explore the ocean. Most deep-sea surveys are conducted using sonar, which provides general topographical information, but can't distinguish between natural and artificial materials. Visual inspection is limited to tiny areas, brief glimpses through the viewports of submersibles or the cameras of remotely operated vehicles. We see only fragments, isolated details without the context needed to interpret them properly. Even when we find obviously artificial objects on the ocean floor, they usually turn out to be relatively recent. Shipwrecks, discarded equipment, lost cargo. Our expectations have been calibrated by these modern artifacts, so we know what recent human technology looks like after exposure to seawater, but we have no reference points for what ancient space technology might look like after millions of years of oceanic processing. The biological environment of the deep ocean might actually preserve certain kinds of evidence better than terrestrial environments. The cold temperatures, high pressure, and low oxygen levels in deep water can slow decomposition dramatically. Organic materials that would decay quickly on land might survive for much longer periods on the ocean floor, especially if they were buried rapidly by sediment. But preservation is only half the problem. The other half is recognition. If ancient spacecraft were built using biological materials or biomechanical hybrids, their remains might be virtually indistinguishable from natural organic deposits. If their propulsion systems were based on principles we don't understand, their waste products might appear to be unusual but natural chemical formations. The ocean also offers possibilities for active concealment. If some ancient spacefaring civilization had developed underwater habitats, they might have built their installations in locations specifically chosen to remain hidden from surface observation. Deep ocean trenches, underwater caverns, areas of the seafloor that are geologically stable but difficult to access. Such installations might still exist, camouflaged by millions of years of marine growth, their original functions obscured by biological colonization and geological processes. They might even be active, powered by geothermal energy or chemical processes that tap the ocean's own resources, carrying out automated functions according to programming established millions of years ago. The ocean's hidden history represents perhaps the largest gap in our understanding of Earth's past. If intelligence has arisen multiple times on this planet, and if some of those civilizations achieved spaceflight, the ocean is the most likely place where evidence of their activities might still exist. But it is also the place where we are least likely to find it, not because it isn't there, but because we lack the tools and techniques to search effectively in an environment that covers most of our planet's surface and remains largely unexplored. Beneath the waves, the ancient past might still be present, waiting in the darkness for explorers who know how to look beyond the assumptions that limit our current search methods. When we imagine technological development, we tend to think in terms of metal and silicon, rockets and computers, the hard materials and precise engineering that characterize our own approach to complex problems. But there's another path that intelligence might take, one that works with living systems rather than against them, that grows solutions rather than manufacturing them, that treats biology not as something to be overcome but as the ultimate technology to be refined and directed. Consider how different our world might look if we developed along biological rather than mechanical lines. Instead of mining metals from the earth, we might have cultivated organisms that could concentrate and purify any element we needed from seawater or soil. Instead of burning fossil fuels for energy, we might have developed symbiotic relationships with organisms that could capture and store solar energy far more efficiently than any photovoltaic cell. Instead of manufacturing complex materials in high-temperature furnaces, we might have guided biological processes to grow materials with properties that exceed anything we can currently produce artificially. This isn't pure speculation. We already see hints of such possibilities in the natural world. Some bacteria can precipitate metals from solution, creating pure deposits of gold, silver, or platinum. Certain organisms can produce materials stronger than steel, more flexible than rubber, more transparent than glass. Others can generate electrical fields, manipulate magnetic forces, or survive in environments that would destroy any artificial device. If an ancient civilization had pursued this biological approach to technology, their spacecraft might have been living entities rather than mechanical constructs. These bioships could have grown from engineered organisms, their hulls secreted like shells, their internal systems functioning like organs, their propulsion based on biological processes we can barely imagine. Such vessels would have advantages over mechanical spacecraft that become obvious once you consider the challenges of long-duration space travel. Mechanical systems wear out, break down, and require replacement parts that must be carried from the beginning of the journey. Biological systems, by contrast, can repair themselves, adapt to changing conditions, and even evolve new capabilities during extended missions. A biospacecraft might literally grow larger as its mission progressed, adding new sections to house expanding crews or to accommodate new functions that became necessary during the journey. Its hull might become thicker and more resistant to radiation as it encountered more dangerous environments. Its internal atmosphere might adjust its composition automatically to optimize the health and performance of its occupants. The propulsion systems of such vessels might work by manipulating biological processes that we don't yet understand. Some organisms can generate thrust by expelling water or other fluids, while others can manipulate their buoyancy to rise or sink through liquid media. Scaled up and adapted for space, such mechanisms might provide propulsion without the need for chemical rockets or reaction mass. Even more exotic possibilities emerge when we consider that biological systems routinely manipulate forces and fields that we can barely detect with our most sensitive instruments. Living cells generate electrical potentials, create magnetic fields, and seem to influence quantum processes in ways that suggest they have access to energy sources we haven't identified. A civilization that understood these biological phenomena deeply might have developed propulsion systems based on direct manipulation of gravitational or electromagnetic fields. The manufacturing base for such a civilization would look nothing like our industrial infrastructure. Instead of factories and assembly lines, they might have had biological foundries, specialized organisms designed to produce specific materials or components through guided metabolic processes. Instead of mining operations, they might have had cultivation farms where useful elements were concentrated from dilute sources through biological extraction. Their spacefaring infrastructure might have been largely biological as well, launch facilities that were literally grown rather than built, using organisms that could shape themselves into the precise configurations needed for optimal spacecraft deployment. Navigation systems based on biological sensors more sensitive than any artificial instrument, capable of detecting gravitational gradients, magnetic field variations, or chemical traces across interplanetary distances. The archaeological traces of such a civilization would be completely different from what we expect to find. No metal debris from failed launches, no chemical residues from rocket fuel, no electronic components corroding in ancient ruins. Instead, we might find fossilized organisms with unusual properties, biological structures that seem too complex or too purposeful to have evolved naturally, or chemical signatures that suggest biological processes operating on scales and with purposes that don't match anything in the current biosphere. We might already have found such evidence without recognizing it. Unusual fossil formations that we classify as extinct species might actually be the remains of engineered organisms. Strange mineral deposits that we attribute to unknown geological processes might be the waste products of biological manufacturing systems. Chemical anomalies in ancient rocks might represent the signatures of biotechnological processes that operated millions of years ago. The advantage of biological technology is also its greatest challenge for archaeological detection. Living systems are designed to integrate with their environments, to use available resources efficiently, and to minimize waste. A biological space program would leave few obvious traces because it would be designed to work in harmony with natural processes rather than against them. Such a civilization might have achieved spaceflight not by conquering nature, but by becoming more natural, more integrated with biological systems, more dependent on living processes for their technology. Their departure from Earth might not have required the dramatic violence of chemical rockets, but the subtle elegance of biological systems that simply grew beyond the boundaries of the planetary surface. And if they succeeded, if they learned to live in space using biological rather than mechanical technology, they might still be there, spread throughout the solar system in forms so integrated with natural processes that we don't recognize them as artificial. The boundary between life and technology, between natural and artificial, might have dissolved entirely, leaving behind not abandoned ruins but living systems that continue to function millions of years after their original creators moved on to other concerns. Between Mars and Jupiter lies a region of space that has puzzled astronomers since its discovery. The asteroid belt contains millions of rocky fragments, from pebble-sized debris to objects hundreds of miles across, all orbiting the Sun in a broad band that seems to represent the remnants of something that was once much larger and more organized. The conventional explanation is that these are the leftover building materials from the early solar system, planetesimals that never quite managed to coalesce into a full planet due to Jupiter's gravitational interference. But there are oddities in the asteroid belt that don't quite fit this neat narrative. Some asteroids have compositions that don't match what we'd expect from natural planetary formation. Others orbit in patterns that seem too regular, too organized to be purely the result of random gravitational interactions over billions of years. A few show surface features that look almost geometric when viewed through our most powerful telescopes, straight lines and angular formations that could be natural fracture patterns, but might represent something else entirely. The asteroid Vesta, for example, has a massive crater at its south pole that's so large it almost split the entire body in two. The impact that created this crater should have scattered debris throughout the solar system, and indeed, we've found meteorites on Earth that appear to have come from Vesta. But the crater itself has an unusual structure, with a central peak and terraced walls that are more complex than we'd expect from a simple impact event. Then there's Ceres, the largest object in the asteroid belt, now classified as a dwarf planet. When the Dawn spacecraft arrived there in 2015, it found bright spots on the surface that initially defied explanation. These spots turned out to be deposits of salt, apparently left behind by subsurface water that had evaporated. But the distribution of these spots is curious, clustered in certain areas while absent from others, creating patterns that look almost deliberate. More intriguing are the asteroids with highly unusual orbits. Most asteroid belt objects follow roughly circular paths around the Sun, but some trace elongated ellipses that take them far from their neighbours, out toward the orbits of other planets, or inward toward the inner solar system. A few have retrograde orbits, moving in the opposite direction from the majority of solar system objects. These orbital anomalies could be natural, the result of gravitational perturbations from Jupiter and other massive bodies over billions of years. But they could also represent something else, the remains of artificial objects, spacecraft or space stations that were once part of a coordinated system, but have since been scattered by time and gravitational forces into the seemingly random distribution we observe today. If an ancient Earth civilization had established a presence in the asteroid belt, they would have had excellent reasons for doing so. The belt contains an enormous wealth of rare metals and other valuable materials, much of it in forms that would be easier to process in the low-gravity environment of space than in the deep gravity well of a planetary surface. Water ice is abundant in many asteroids, providing both fuel and life support for space-based operations. The low gravity and lack of atmospheric interference would make it an ideal location for large-scale construction projects or industrial processes that would be impossible on Earth. A spacefaring civilization might have built mining stations, manufacturing facilities, even cities among the asteroids. They might have redirected asteroids into more convenient orbits, clustering resources where they could be most easily accessed. They might have constructed massive installations using asteroid materials, taking advantage of the abundant raw materials and the forgiving environment for large-scale engineering projects. Over millions of years, such installations would be subject to the same forces that affect natural asteroids: impact from smaller debris, gradual orbital decay due to gravitational perturbations, the subtle but persistent effects of solar radiation pressure. Artificial structures would be broken apart, scattered, and mixed with natural materials until they became indistinguishable from the general population of asteroid belt objects. But some traces might remain. Asteroids with unusual compositions that reflect industrial processes rather than natural formation. Objects with densities that don't match their apparent composition, suggesting hollow interiors or unusual internal structures. Fragments that show signs of having been worked or modified, even if the original purpose is no longer clear. The challenge is that we have examined only a tiny fraction of asteroid belt objects in any detail. Most of our knowledge comes from telescopic observations that can tell us about size, orbit, and general composition, but very little about structure or surface features. The few asteroids we've visited with spacecraft have revealed surprising complexity, but they represent a vanishingly small sample of the millions of objects in the belt. There's also the question of scale. If ancient installations in the asteroid belt were truly massive, built over thousands or millions of years by a civilization with access to essentially unlimited raw materials, they might have grown to sizes that dwarf anything we can currently imagine. What we interpret as large asteroids might actually be the remains of artificial structures so vast that we lack the conceptual framework to recognize them as constructions rather than natural objects. The asteroid belt might be less a collection of leftover planetary building blocks and more a debris field, the scattered remains of an ancient space-based civilization that once thrived in the space between Mars and Jupiter. The regular spacing of some orbital groups, the unusual compositions of certain objects, the geometric features visible on some surfaces, all of these might be clues to a presence that was once organized and purposeful, but has been rendered nearly invisible by the patient work of time and gravity. If this interpretation has any validity, then the asteroid belt represents not just a resource for future human expansion into space, but a library, a museum of ancient space technology waiting to be properly understood. The fragments we mine for metals and water might contain information about propulsion systems, construction techniques, or energy sources that could transform our own approach to space travel and space habitation. The moon hangs in our sky, silent and seemingly unchanging, a constant companion that has watched over Earth through billions of years of geological upheaval and biological evolution. Unlike our planet, with its active atmosphere, flowing water, and dynamic geology, The Moon is a repository of pristine history. Its surface bears the scars of every major impact, preserves the footprints of every visitor, and maintains a record that stretches back to the earliest days of the solar system. This makes the Moon perhaps the most promising place to search for evidence of ancient spacefaring civilizations. While Earth's surface is constantly recycled through weathering, erosion, and plate tectonics, the lunar surface changes only through the slow accumulation of micrometeorite impacts and the occasional larger collision. Anything placed there millions of years ago might still be there, waiting to be discovered by explorers who know how to look beyond the obvious features that dominate the landscape. We've barely scratched the surface of lunar exploration. The Apollo missions visited only 6 locations, all chosen for their safety and accessibility, rather than their archaeological potential. The sites were concentrated in a narrow band near the lunar equator, avoiding the more challenging but potentially more interesting polar regions, the deep craters that never see sunlight, and the rugged highlands that might harbour older secrets. Even the areas we did visit were explored only superficially. The astronauts spent at most a few days on the surface, travelling only a few miles from their landing sites, collecting samples from easily accessible locations. The total area of the Moon that has been examined by human eyes amounts to a few square miles out of the nearly 15 million square miles of lunar surface. The far side of the Moon, perpetually hidden from Earth, remains almost entirely unexplored. We have satellite images that show the major topographical features, but we have no detailed knowledge of surface composition, no close examination of unusual formations, no understanding of what might be concealed in the deep shadows of craters and valleys that never receive direct sunlight. This hidden hemisphere might be where ancient visitors would have established their most important installations. Protected from Earth observation, shielded from solar radiation by the Moon's bulk, accessible to spacecraft approaching from the outer solar system, the far side would offer advantages for any civilization that wanted to maintain a presence near Earth, while remaining undetected by surface-based observers. The lunar environment, harsh as it seems to us, might actually have been ideal for certain kinds of ancient technology. The vacuum of space eliminates corrosion and weathering. The lack of atmospheric interference allows clear observation of celestial objects. The low gravity makes large-scale construction projects much more manageable than they would be on Earth. The abundance of rare metals in lunar rocks provides raw materials for advanced technologies. Most importantly, the Moon's slow rotation means that any installation could be designed for either permanent solar illumination or permanent shadow, depending on its requirements. Solar-powered facilities could be located near the poles where sunlight is nearly continuous, while installations requiring protection from solar radiation could be placed in permanently shadowed regions. The traces left by ancient lunar installations might be subtle but durable. Tracks and footprints in lunar dust protected from wind and weather could persist for millions of years. Artificial structures, built to withstand the temperature extremes and radiation environment of the lunar surface, might remain recognizable even after geological ages. More intriguing are the possibilities for active traces. If ancient civilizations had built automated systems designed to operate for extended periods, some of those systems might still be functional. The lunar environment is harsh for biological systems, but potentially ideal for certain kinds of technology. Electronic devices, if properly shielded and designed for the environment, could continue operating for millions of years with minimal maintenance. Such systems might be designed to remain dormant unless activated by specific signals or conditions. They might be monitoring Earth, waiting for signs that another spacefaring civilization had emerged. They might be relay stations, part of a communication network that spans the solar system. They might be observers, recording data about solar system evolution and storing it against some future need. The challenge is that we wouldn't necessarily recognize such systems as artificial. Millions of years of micrometeorite bombardment would alter their appearance, covering them with accumulated dust and debris. Solar radiation and thermal cycling might cause some components to fail while leaving others functional. The overall configuration might be so changed by time and environment that the original purpose would be completely obscured. We might already have photographed evidence of ancient lunar installations without recognizing what we were looking at. Satellite images show numerous features that could be natural formations, but might represent something else entirely. Straight line formations that could be geological fractures or artificial structures. Circular features that could be impact craters or the remains of constructed installations. Geometric patterns that could be the result of natural processes or evidence of purposeful design. The Apollo missions brought back hundreds of pounds of lunar samples, but these were collected from only a few locations and analysed primarily for their geological significance. If some of those samples contained artificial materials, traces of ancient manufacturing processes or exotic alloys that don't occur naturally, would we have recognised them as evidence of technology? Or would we have classified them as unusual but natural phenomena, filing them away as curiosities to be explained by future research? The Moon represents our best opportunity to find clear, unambiguous evidence of ancient spacefaring civilizations. Unlike Earth, where such evidence would be buried, eroded, or recycled by geological processes, the lunar surface preserves everything that has ever been placed there. Unlike the asteroid belt, where distances are vast and objects are difficult to reach, the Moon is close enough for detailed exploration with current technology. But finding such evidence requires more than just returning to the Moon. It requires a systematic search guided by new questions, informed by the possibility that we might not be the first intelligence to establish a presence there. It requires looking beyond the familiar features that have dominated our attention and examining the Moon as an archaeological site, a place where the history of intelligence in the solar system might be written in stone and metal and the patient dust of ages. The question of energy haunts every discussion of space travel, ancient or modern. The numbers are unforgiving. To escape Earth's gravity, well requires enormous amounts of energy, roughly 62 megajoules per kilogram of payload. Our current chemical rockets achieve this through brute force, burning vast quantities of fuel to produce the thrust needed for orbital velocity. But chemical propulsion is wastefully inefficient, with most of the energy going into accelerating fuel rather than payload, creating a tyrannical equation where larger missions require exponentially more resources. Any ancient civilization attempting space travel would have faced these same fundamental energy requirements. The laws of thermodynamics haven't changed over geological time. The amount of energy needed to reach orbital velocity was the same 100 million years ago as it is today. But the sources and methods for harnessing that energy could have been radically different. Consider the energy reservoirs available to a planetary civilization. The Earth's rotation contains kinetic energy equivalent to about 2.6 times 10 to the power of 9 joules, more than humanity has used in its entire history. The planet's magnetic field stores roughly 10 to the power of 5 joules of energy. Tidal forces, generated by the Moon's gravitational pull, dissipate about 3.7 times 10 to the power of 12 watts continuously. The temperature difference between the Earth's core and surface drives convection currents that move entire continents, Most of these energy sources are too diffuse or too steady for us to tap effectively with current technology. We lack the engineering capability to harness planetary rotation or extract useful work from geomagnetic fields. But a civilization with different technological insights might have developed methods we haven't imagined for coupling with these vast energy reservoirs. Biological systems offer particularly intriguing possibilities. Living organisms routinely accomplish energy transformations that surpass our best artificial systems. Photosynthesis converts sunlight to chemical energy, with remarkable efficiency across the entire visible spectrum. Some bacteria derive energy from chemical gradients so subtle our instruments can barely detect them. Certain organisms can concentrate and organize energy in ways that produce effects far out of proportion to the apparent energy input. If an ancient civilization had developed biological energy systems to their full potential, they might have had access to power sources that dwarf anything we can currently generate. Engineered organisms that could tap the Earth's magnetic field directly, biological systems that could harness the energy of tidal forces or geothermal gradients, living components that could convert various forms of environmental energy into concentrated, usable power for spacecraft propulsion. The scaling possibilities are particularly striking when considered over geological time periods. A civilization with millions of years to develop their energy infrastructure could have built systems of incredible complexity and capability. Planetary-scale installations that gradually accumulated energy over centuries or millennia, storing it in forms that could be released rapidly when needed for spacecraft launches. Such energy storage systems might not resemble anything we would recognize as technology. They might be integrated into geological structures, biological systems, or hybrid biomechanical networks that span continents. The energy might be stored as gravitational potential in carefully arranged masses, as chemical potential in biological systems, or as field configurations that can be maintained almost indefinitely with minimal energy input. The release mechanisms for such stored energy might be equally exotic. Instead of combustion chambers and rocket nozzles, an ancient civilization might have used resonance effects to tap stored energy, field interactions to convert potential to kinetic energy, or biological systems that could channel enormous power flows through living tissue without damage. Even more speculative possibilities emerge when we consider that consciousness itself might interact with physical systems in ways we don't understand. If awareness can influence quantum processes, if intention can affect the behavior of matter at subtle levels, if there are energies associated with living systems that we haven't identified, then a civilization that understood these phenomena might have had access to propulsion methods that seem to violate our current understanding of physics. The archaeological traces of such energy systems would be difficult to recognize and interpret. Biological components would decompose, leaving at most chemical signatures that we might mistake for natural processes. Geological installations might appear to be unusual mineral formations. Field generators might leave no trace other than subtle alterations in local magnetic or gravitational conditions. We might already have encountered evidence of ancient energy systems without recognizing their significance. Unusual mineral deposits that seem to concentrate specific elements in patterns that don't match known geological processes. Biological formations that appear to channel or focus natural energy flows in ways that seem too organized to be entirely natural. Geological structures that exhibit properties suggesting they were shaped by forces or processes we don't fully understand. The energy requirements for space travel are absolute, but the methods for meeting those requirements are limited only by our understanding of physical law and our engineering capability. An ancient civilization with different insights and different technological approaches might have solved the energy problem in ways that seem impossible from our current perspective, but which represent simply different applications of the same fundamental principles that govern all energy transformations in the universe. If such solutions existed, if some previous Earth civilization had learned to harness planetary-scale energy sources for space propulsion, then the traces of their achievement might still surround us, embedded in the landscape, integrated into natural systems, waiting to be recognized not as curiosities or anomalies, but as evidence of engineering on a scale we have yet to imagine. There's a concept in evolutionary biology known as the Great Filter, a hypothetical barrier so difficult to overcome that it prevents most life from reaching advanced stages of development. The idea suggests that somewhere between the emergence of life and the establishment of galaxy-spanning civilizations, there exists a challenge so formidable that virtually all species fail to surpass it. The question that haunts researchers is whether this filter lies behind us, in our past, or ahead of us, waiting in our future. Applied to the possibility of ancient spacefaring civilizations on Earth, the Great Filter concept takes on a particularly unsettling dimension. If intelligence capable of space travel has emerged on Earth before, why do we see no evidence of thriving space-based civilizations? Why do the skies seem empty of artificial structures, communication signals, or ongoing activity by previous Earth species that achieved spaceflight? One possibility is that reaching space represents not a triumph, but a transformation so profound that it fundamentally changes what a civilization becomes. The transition from planetary to space-based existence might be irreversible, not because return is impossible, but because the experience of living in space alters consciousness, priorities, and identity in ways that make planetary concerns increasingly irrelevant. Consider what extended space habitation does to perspective. When you can see your home planet as a small blue dot suspended in infinite darkness, when you experience firsthand the vastness of the cosmos and the insignificance of local concerns, when you have access to resources and energy on scales that dwarf planetary limitations, the priorities that drove your initial expansion into space might fade into distant memory. A civilization that began space exploration to solve resource problems or escape environmental catastrophes might discover that space offers such abundance that scarcity becomes an incomprehensible concept. A species that reach for the stars to ensure survival might find that space-based existence provides security so complete that the original fears seem quaint and primitive. The psychological effects might be even more profound than the material ones. Space dwellers would experience time differently, measured not in seasonal cycles, but in orbital periods and stellar events. Their sense of scale would expand to encompass not just planetary geography, but stellar distances and galactic structures. Their understanding of mortality would shift as they gained access to resources and technologies that could extend individual lifespans far beyond biological limits. Such beings might maintain a distant interest in their planet of origin, monitoring its development and occasionally intervening in critical moments, but they would no longer be citizens of that world in any meaningful sense. They would have become something else entirely, as different from their surface-dwelling ancestors as modern humans are from the earliest life forms that emerged from primordial oceans. This transformation might explain why spacefaring civilizations seem to vanish from the perspective of planetary observers. They don't die out or fail catastrophically. Instead, they graduate to a form of existence so removed from planetary concerns that they become effectively invisible to those still bound to surface environments. The Great Filter, in this interpretation, isn't a barrier that destroys civilizations, but a threshold that transforms them beyond recognition. Crossing it successfully means leaving behind not just the physical constraints of planetary existence, but the entire conceptual framework that defines planetary consciousness. But there's a darker possibility. What if the Great Filter operates in the opposite direction? What if achieving space travel consistently leads to consequences that ultimately doom civilizations rather than liberating them? The very capabilities required for large-scale space colonization, sophisticated resource extraction, planetary-scale engineering might also enable forms of destruction that terrestrial civilizations can't achieve. A species capable of redirecting asteroids for mining might also be capable of using those same asteroids as weapons. A civilization that can manipulate planetary atmospheres for terraforming might also trigger runaway climate changes that sterilize worlds. The energy systems required for interstellar travel might be prone to catastrophic failures that eliminate entire solar systems. Space travel might represent not the solution to civilizational challenges, but their ultimate amplification. The same technologies that promise infinite expansion and eternal survival might carry risks so severe that their development inevitably leads to self-destruction. Every civilization that reaches the threshold of space-based existence might discover too late that they have also reached the threshold of total annihilation. This would explain the silence of space perfectly, not because spacefaring civilizations become invisible, but because they become extinct. The Great Filter would lie precisely at the moment of apparent triumph, the point where civilizations develop the capability to spread throughout the galaxy, but also the capability to destroy themselves more completely than would ever be possible while confined to a single world. From this perspective, the absence of evidence for thriving ancient space civilizations becomes not a puzzle, but a warning. Every previous attempt to transcend planetary limitations might have ended in catastrophe so complete that even the memory of the attempt was erased. The silence we hear when we listen for signs of ancient spaceflight might be the echo of destructions so thorough that they left no trace except emptiness. The implications for our own spacefaring ambitions are sobering. If the Great Filter lies ahead of us, if the transition to space-based civilization consistently proves fatal, then our current expansion beyond Earth might be not the beginning of a glorious future, but the approach to an inevitable end. Or perhaps the filter works both ways simultaneously. Perhaps some civilizations successfully transcend to space-based existence, while others destroy themselves in the attempt. The successful ones become invisible through transformation, while the failures become invisible through extinction. Either way, the result is the same: a universe that appears empty, but might actually be full of intelligences we can no longer recognize, or ruins too scattered to detect. When we examine the history of life on Earth, we find patterns that seem almost too precise to be accidental. The emergence of complex cells, the development of multicellular organisms, the appearance of nervous systems and eventually consciousness, all of these represent quantum leaps in biological organization that occurred at remarkably specific intervals. Some researchers have noted periodicities in evolutionary development that suggest underlying cycles, as if intelligence arises, flourishes, and transforms according to rhythms deeper than individual species or even geological epochs. The fossil record shows distinct periods of rapid evolutionary innovation followed by long stretches of relative stability. The Cambrian explosion, roughly 540 million years ago, saw the sudden appearance of most major animal phyla in a geological instant. The development of complex brains and sophisticated behaviors occurred in multiple lineages simultaneously during certain periods, then seemed to plateau for millions of years before the next surge of innovation. These patterns could represent natural selection responding to environmental pressures, random mutations creating opportunities for complexity, or the inherent tendency of information processing systems to become more sophisticated over time. But they could also reflect something more systematic, cycles of intelligence emerging, reaching certain developmental thresholds, and then either transcending to new forms of existence or collapsing back to simpler states. If consciousness and intelligence are emergent properties of sufficiently complex systems, then perhaps they emerge cyclically as complexity builds to critical thresholds. Each cycle might produce civilizations that explore different approaches to the fundamental challenges of existence: space travel, resource management, the relationship between individual and collective consciousness. Some approaches might prove sustainable over cosmic timescales, while others might lead to transformation or extinction after relatively brief periods. The genetic code itself contains mysteries that hint at possible intervention or guidance by previous intelligences. The mathematical relationships embedded in DNA, the error correction mechanisms that seem more sophisticated than random evolution should produce, the apparent optimization for information storage and retrieval that exceeds what natural selection alone might achieve. All of these suggest that the development of life on Earth might have been influenced by intelligences working on timescales far longer than individual species' lifespans. Certain aspects of human genetics seem particularly puzzling from a conventional evolutionary perspective. The rapid expansion of brain size over the last few million years occurred faster than typical evolutionary processes can easily explain. The development of a language capabilities required neural structures so complex and specialized that their appearance through random mutation and selection seems statistically improbable. The human capacity for abstract thought, mathematical reasoning, and artistic expression far exceeds what would be necessary for basic survival in ancestral environments. These anomalies could represent the normal operation of evolutionary processes under specific environmental pressures, but they could also reflect genetic modifications introduced by previous spacefaring civilizations, interventions designed to accelerate the development of intelligence in species showing potential for eventual space travel themselves. Such interventions wouldn't necessarily be obvious or detectable through conventional genetic analysis. Advanced bioengineering might work by introducing subtle modifications that guide normal evolutionary processes rather than replacing them, creating developmental trajectories that appear natural but are actually directed towards specific outcomes. The goal wouldn't be to create immediate spacefaring capability, but to establish the genetic and neurological foundations that would make such capability more likely to emerge over evolutionary time. The modifications might be designed to activate only when environmental conditions become appropriate, remaining dormant for millions of years until triggered by specific technological or social developments. This could explain the apparent universality of certain mathematical and physical insights across human cultures. If our neural architecture has been optimized for understanding the principles underlying space travel, navigation between worlds, and the manipulation of cosmic-scale forces, then we might be genetically predisposed to discover these principles, regardless of our specific cultural or historical circumstances. The recent acceleration of human technological development might represent the activation of these dormant genetic programs. Our sudden transition from agricultural to industrial to spacefaring civilization over just a few centuries could be the natural result of neural modifications introduced millions of years ago, designed to trigger rapid technological advancement when certain prerequisites were met. From this perspective, our drive to explore space isn't just curiosity or survival instinct, but genetic memory, the expression of modifications introduced by previous civilizations that achieved space travel themselves. We're not pioneering new territory, but following pathways that have been prepared for us by intelligence that understood the challenges we would face and the capabilities we would need. The cyclical nature of this process suggests that intelligence might be a cosmic phenomenon rather than a planetary accident, something that emerges naturally from the complexity of evolving systems but follows patterns that span multiple worlds and stellar lifetimes. Each cycle might build on the achievements of previous cycles, with spacefaring civilizations serving as gardeners, planting the genetic seeds that will eventually produce new generations of spacefaring species. If this interpretation has any validity, then we're not just exploring space for our own purposes, but fulfilling a role in a much larger pattern, continuing a cycle that has been operating since the early days of the galaxy. Our achievements in space travel might eventually lead us to the same realization that guided our predecessors, that intelligence is not something that belongs to individual species, but something that flows through them, using biological evolution as a vehicle for its own cosmic development. Ancient peoples understood time differently than we do. To us, time is linear, progressive, moving from a primitive past toward an ever-improving future. But many of the world's oldest cultures saw time as circular, cyclical, an eternal wheel where patterns repeat across vast scales, where what has been will be again, where endings are always beginnings in disguise. The Hindu concept of cosmic cycles describes vast periods of time called kalpas, each lasting billions of years, during which the universe passes through phases of creation, preservation, destruction, and renewal. Within these great cycles are smaller cycles, yugas, spanning hundreds of thousands of years, each characterized by different levels of consciousness and technological capability. According to these traditions, we are currently in the Kali Yuga, the age of darkness and ignorance, but this period will eventually give way to a new golden age when knowledge and wisdom flourish again. The Maya developed calendrical systems of extraordinary complexity, tracking multiple overlapping cycles that range from days to periods longer than recorded human history. Their long-count calendar measures time in units that extend millions of years into the past and future, suggesting a conception of history that spans geological epochs rather than mere human generations. These aren't isolated examples. Celtic traditions speak of the Wheel of the Year and the Great Wheel of Ages. Norse mythology describes cycles of destruction and renewal, where entire worlds are destroyed and reborn. Even ancient Greek philosophy recognized cyclical time, with thinkers like Empedocles and the Stoics proposing that cosmic history repeats itself in eternal cycles. From our modern scientific perspective, these cyclical concepts of time seem primitive, unscientific, inconsistent with our understanding of entropy and the arrow of time. But what if these ancient traditions preserved genuine insights about patterns operating on scales too vast for us to perceive directly? What if intelligence really does emerge in cycles, rising and falling according to rhythms that span millions of years? The geological record shows clear evidence of cyclical patterns in Earth's history. Ice ages come and go with predictable regularity. Mass extinctions occur roughly every 26 million years, possibly triggered by the solar system's passage through different regions of the galaxy. Ocean chemistry, atmospheric composition, and magnetic field strength all fluctuate according to cycles that operate over millions of years. If intelligence emerges from the complexity of natural systems, it might be subject to the same kinds of cyclical patterns that govern other planetary phenomena. Periods when environmental conditions favour the development of complex consciousness might alternate with periods when such development becomes impossible or unsustainable. During favourable periods, intelligence might emerge rapidly, develop sophisticated technologies, achieve space travel, and establish civilizations that span the solar system. But these periods of flourishing might be followed inevitably by periods of decline, when environmental changes make advanced civilization untenable, forcing intelligence to retreat, simplify, or disappear entirely. The cyclical model suggests that what we call prehistory might actually be post-history, the aftermath of previous cycles of civilization that rose to heights we're only beginning to approach. The Stone Age might not represent humanity's primitive beginnings, but the remnant phase of a much more sophisticated cycle that had exhausted its possibilities and was beginning the long process of renewal. Our own rapid technological development over the last few centuries might mark not the first emergence of advanced technology on Earth, but the return phase of a cycle, the reawakening of capabilities that had been dormant during a period of civilizational winter. The principles we're discovering in physics, chemistry and biology might be rediscoveries, insights that had been achieved before and then lost during the transition between cycles. This would explain the remarkable speed of our technological acceleration. Instead of building knowledge from nothing, we might be recovering information that already exists in some form, encoded in the structure of the universe itself, waiting to be rediscovered by minds sophisticated enough to recognize it. The mythological traditions that speak of golden ages in the past, of gods who walked among humans and shared advanced knowledge, might be cultural memories of previous cycles when spacefaring civilizations were active on Earth. The promise of return, the expectation that the gods will come back someday, might reflect not religious hope, but practical memory of cyclical patterns that operate with cosmic regularity. If civilizations really do rise and fall in predictable cycles, then our current spacefaring ambitions might be part of a much larger pattern. We might be approaching the peak of our cycle, the point where we achieve maximum expansion and capability before beginning the inevitable transition to whatever comes next. The question becomes whether understanding these cycles gives us any power to influence them. If we recognize that we're part of a recurring pattern, can we find ways to extend the creative phase to avoid the decline that seems to have claimed previous iterations? Or are these cycles as inevitable as the seasons, natural rhythms that operate beyond the control of any individual civilization? The ancient traditions suggest that knowledge of the cycles themselves might be part of what gets preserved and transmitted between iterations. The civilizations that achieve the deepest understanding of cosmic patterns might find ways to seed future cycles with information that helps subsequent civilizations develop more quickly and sustainably. From this perspective, our exploration of space might serve a purpose larger than our own expansion and survival. We might be preparing to plant the seeds of future cycles, ensuring that whatever comes after us will have access to the knowledge we've gained about the universe and our place within it. When we look up at the night sky, we expect to see signs of intelligence if it exists in abundance. We listen for radio signals, search for artificial structures, scan for the waste heat of massive engineering projects. We assume that any civilization capable of space travel would be actively communicating, building, expanding, leaving traces that we could detect across interstellar distances. But the cosmos appears largely silent, empty of the chatter and construction we might expect from a galaxy teeming with technological civilizations. This silence extends to our own solar system as well. If previous Earth civilizations had achieved spaceflight millions of years ago, why don't we see evidence of their ongoing activities? Where are the space stations, the mining operations, the communication networks that such civilizations would presumably have established? Why does space seem so pristine, so unmarked by intelligence? The conventional answer is that intelligence capable of spaceflight is extraordinarily rare, that we may be the first and possibly only example in our local galactic region. But there's another possibility that's both more hopeful and more unsettling. Space may not be empty at all. It may be full of intelligence, but intelligence so advanced, so perfectly adapted to the cosmic environment that we lack the conceptual framework to recognize it. Consider what happens to intelligence over cosmic timescales. A civilization that achieves spaceflight doesn't remain static. It continues to develop, to adapt, to evolve in response to the unique challenges and opportunities of the space environment. After millions of years of space-based existence, such a civilization would be as different from its planetary origins as we are from the first microorganisms that emerged in primordial seas. The constraints of the space environment would shape this evolution in specific directions. Energy must be used efficiently across vast distances and timescales. Materials must be recycled with perfect precision, since waste disposal becomes impossible when you're travelling between stars. Information must be preserved and transmitted across generations that may span thousands of years. These constraints would favour forms of intelligence that are patient, distributed, conservative of resources, and capable of thinking in terms of cosmic rather than planetary timescales. Such beings would likely operate on schedules measured in millions of years, implementing projects that span multiple stellar lifetimes, pursuing goals that are invisible to creatures confined to single worlds and brief biological lifespans. Their technology would probably be indistinguishable from natural phenomena to observers like us. Instead of building crude mechanical structures that fight against cosmic forces, they would learn to work with those forces, to guide and channel natural processes rather than opposing them. Their installations might look like unusual asteroid formations, their spacecraft like comets with slightly irregular orbits, their communication systems like natural magnetic or gravitational field variations. They might be everywhere around us, integrated so completely with natural systems that we perceive them as part of the background structure of the universe, rather than as artificial constructs. The dark matter that makes up most of the cosmos, the cosmic rays that permeate interstellar space, the magnetic fields that organize galactic structure, any or all of these might be partially artificial. The infrastructure of civilizations so advanced that they've learned to work on the scale of fundamental forces. This interpretation transforms our understanding of cosmic silence. Instead of indicating absence, the quiet we observe might indicate perfection, intelligence that has learned to operate without waste, without unnecessary signals, without the crude emissions that characterize early technological civilizations like our own. The emptiness we see might be fullness so complete that it appears invisible to minds still trapped in planetary thinking patterns. From this perspective, our search for extraterrestrial intelligence has been looking in the wrong places and asking the wrong questions. We've been scanning for radio signals when we should be analysing gravitational anomalies. We've been searching for megastructures when we should be studying the fine structure of interstellar space itself. We've been listening for crude artificial transmissions when we should be learning to recognise the subtle orchestration of cosmic forces by intelligences that work on galactic scales. The silence of space might not be silence at all, but a conversation conducted in languages we haven't learned to speak, using media we haven't learned to perceive, discussing topics we haven't learned to contemplate. The ancient Earth civilizations that achieved spaceflight might still be active, still present, still engaged in projects of cosmic scope and significance, but operating at levels of sophistication that render them invisible to creatures still struggling with the basic challenges of leaving a single planetary surface. They might be watching our current efforts with the patient interest that we bring to observing the development of complex behaviors in other species. Our rockets and satellites might seem to them like the first tentative steps of an intelligence beginning to awaken to cosmic possibilities, worthy of gentle guidance but not direct intervention, much as we might watch young animals learning to navigate their environment without disrupting the natural learning process. The vast emptiness of space might be instead a vast fullness, organized and inhabited by minds that have learned to think and act on scales that dwarf our current imagination. The silence we hear might be the sound that perfect intelligence makes when it has learned to work in complete harmony with the deep structures of reality itself. If we discover tomorrow that ancient civilizations had indeed reached space, if we found undeniable evidence that we're not the first intelligence from Earth to touch the void between worlds, what would that mean for us? How would such a revelation change our understanding of ourselves, our future, and our place in the vast story of consciousness unfolding across cosmic time? The immediate implications would be both humbling and liberating. Humbling, because it would strip away the assumption of human uniqueness, the belief that our particular combination of intelligence, technology, and ambition represents something unprecedented in Earth's history. We would have to accept that what feels to us like pioneering exploration might actually be a well-travelled path, that the challenges we face in space have been faced before, that the solutions we're developing might be rediscoveries of principles understood millions of years ago. But this humbling would also be liberating. If other Earthborn intelligences had successfully made the transition from planetary to space-based existence, it would prove that such transitions are possible, that the great filter of space travel can be crossed without inevitable extinction or failure. We would no longer be alone in the cosmos, not because we'd found alien civilizations, but because we'd found evidence of our own deeper heritage, our connection to a lineage of spacefaring consciousness that extends far beyond human history. The discovery would transform our approach to space exploration itself. Instead of proceeding through trial and error, learning through costly mistakes and dangerous experiments, we might be able to find guidance from the traces left by our predecessors. Ancient spacecraft debris might contain technologies we haven't imagined. Abandoned installations on the Moon or in the asteroid belt might preserve information about propulsion systems, life support methods, or navigation techniques that could accelerate our own development by centuries or millennia. We might discover that what we consider cutting-edge space technology is actually primitive compared to methods developed by previous civilizations. Our chemical rockets might seem as crude as stone tools compared to the elegant biological or field-based propulsion systems used by ancient spacefarers. Our rigid mechanical spacecraft might appear laughably inefficient compared to self-repairing, adaptive bioships that could evolve during their missions. But the most profound changes would be philosophical rather than technological. The discovery would force us to reconsider fundamental questions about the nature of intelligence, consciousness, and purpose. If spacefaring civilizations arise naturally from planetary ecosystems, if the drive to explore beyond our world of origin is a recurring pattern, rather than a unique human aberration, then consciousness itself might be understood as a cosmic phenomenon, something that emerges not just to survive on individual worlds, but to spread throughout the universe. We might realize that our own consciousness carries within it not just the evolutionary history of life on Earth, but the accumulated experience of previous cycles of intelligence that had already made the journey we're now undertaking. Our dreams of space exploration, our fascination with the stars, our drive to understand the cosmos might be genetic or cultural memories inherited from ancestors who had actually lived among the worlds we're now struggling to reach. This would give new meaning to our spacefaring ambitions. Instead of conquering new territory for human benefit, we might understand ourselves as participating in a larger pattern, fulfilling a role in the cosmic development of consciousness itself. Our missions to other planets wouldn't just be human expeditions, but the continuation of a process that had been underway for millions of years, intelligence exploring itself through the vehicle of space travel. The discovery might also explain some of the strange compulsions that drive human space exploration. The willingness to risk everything for the sake of reaching other worlds, the sense of destiny that many astronauts report feeling, the almost mystical reverence that space travel inspires, all of these could be understood as expressions of deeper memories, the awakening of drives and purposes that were encoded in consciousness during previous cycles of spacefaring development. We might find that our role is not just to explore space for our own species, but to prepare the way for future intelligences, to plant the seeds that will guide the next cycle of consciousness as it emerges from Earth and reaches toward the stars. Our space habitats, our technological developments, our accumulated knowledge about living and working in space might serve as gifts to intelligences not yet born. Just as we might be receiving gift from intelligences that preceded us by millions of years, the realization would place our current civilizational challenges in a completely different context. Our environmental problems, our social conflicts, our struggles with technology and meaning, all of these might be understood as natural growing pains, predictable difficulties that any species faces during the transition from planetary to cosmic consciousness. We might discover that previous civilizations had faced identical challenges and had found ways to resolve them that we haven't yet imagined. Most importantly, the discovery would suggest that consciousness, intelligence, and the drive to explore are not accidents, but fundamental features of the universe, patterns that will continue to emerge and develop regardless of the fate of any individual species or civilization. We would no longer be alone in time, isolated in our brief moment of awareness, but part of an ongoing story of consciousness awakening to itself across cosmic scales. So here we are at the quiet edge of the question, after all the wondering, all the searching, all the long walks, through possibilities that stretch from the deepest ocean trenches to the spaces between stars, and maybe we're left not with answers, but with something more valuable, a different way of seeing, a broader sense of what might be possible in a universe far stranger and more patient than we usually dare to imagine. The question of whether ancient civilizations reach space remains just that, a question. We have no smoking gun, no undeniable artifact, no clear signature that proves beyond doubt that Earth-born intelligence has touched the void before us. The evidence, such as it is, remains frustratingly ambiguous. Every anomaly we've considered has conventional explanations. Every mystery we've explored could be resolved through natural processes we understand or simply haven't yet investigated properly. But perhaps the ambiguity itself is the point. Perhaps the question was never meant to be answered definitively, but to be held gently, like a possibility that opens up space for wonder rather than closing it down with certainty. What we've discovered in asking the question is how much we don't know about our own planet's history, how incomplete our records are, how easy it would be for entire chapters of the story to have been written and erased without leaving obvious traces. We've glimpsed the possibility that intelligence might be less rare and more recurring than we assumed, that consciousness might emerge naturally from complexity not once but many times, following patterns we're only beginning to recognize. We've considered that space travel might not represent conquest but return, not innovation but memory, not uniquely human achievement, but the expression of drives that run deeper than any single species. The implications ripple outward like stones dropped in still water. If we might not be first, then we might not be alone in the deeper sense of being disconnected from our own larger story. We might be part of something ongoing, something that has been developing for millions of years and will continue developing for millions more. This changes how we think about our responsibilities and our failures. If civilizations rise and fall in cycles, then our current anxieties about environmental collapse or technological catastrophe become less existential and more transitional. Not endings, but changes of state, phases in longer processes that operate according to their own deep rhythms. But perhaps most importantly, the question invites us to hold mystery without needing to solve it, to remain curious without becoming obsessed, to wonder without losing our footing in the present moment. Because whatever might have happened in the deep past, we are here now, in this moment, under these same patient stars that have watched over every mind this world has ever produced. And you, right now, wherever you are, you're part of that continuity, part of the long conversation between consciousness and cosmos that might be much older and much larger than we know. Even in listening to these ideas, you're participating in something that connects you not just to other humans, but possibly to other forms of awareness, other experiments in understanding what it means to wake up in a universe full of possibilities. So rest easy with the questions. Let them settle into the quiet spaces of your mind, not as problems to be solved, but as companions for the journey. The past will keep its secrets, space will keep its silence, and the future will unfold according to patterns too large for any of us to see completely. But consciousness will continue, awareness will persist, and somewhere in the vastness of what we don't yet understand, new forms of wonder are always emerging. Sleep well, fellow traveller in time. The stars are patient, the questions are eternal, and you're exactly where you need to be in the long, slow story of intelligence learning to know itself.